Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be continuing our discussion of the atom by picking up Chapter 7, where we're looking at periodicity, periodic properties of elements. Now, first section gets into really the development of the periodic table. Now, remember from pre-AP chemistry, elements in the same group generally have similar chemical properties. And this is really a driving force behind the creation of the first periodic table, because really your first tables of elements were just lists of elements in alphabetical order. And outside of finding information quickly, alphabetical lists really are not that useful in other situations. So Dmitry Mendeleev and Lothar Meyer both independently came to the same conclusion about how elements should be grouped. They were looking for a better way to group elements for their students. Elements were grouped by similarities in chemical properties and by increasing atomic weight. And what they noticed was that certain elements tended to behave chemically similar to other elements. And putting those things together made the um, table of elements much more important, because if you know hydrogen mixes with oxygen 2 to 1, that means anything from the hydrogen and oxygen columns will also mix 2 to 1. So organizing your elements by similar chemical properties made a much more useful periodic table. Now, Mendeleev took it a little bit further. And one of the things he did was he used it as a predictive tool. Now, he knew the properties of elements, and if he stuck to his rules, similar chemical things together and increasing atomic mass, he found that it looked like there were holes in his table. Like if you were organizing a deck of cards by suit and by ace to king, and some of them were missing, you'd end up with blanks in your table when you set it out. And the exact same thing happened to him. And what he said was, I think these are elements that are going to be discovered. So, for example, germanium, which he predicted to have an atomic weight of 72 and a density of 5.5 and so on. A few years after his periodic table was published, somebody actually did discover the element, named it germanium. He called it ecosilicon, but it had properties very, very similar as to what he had predicted they would be. So right away, scientists realized the impressive things you could do with the periodic table that just a list of plain elements couldn't do. So the periodic table became a very useful tool in chemistry. Now, the periodic table never really quite 100% worked when we were organizing it by increasing atomic mass left to right and top to bottom. And that was because it really isn't as much what the mass is the number of protons that you have, which has a huge impact on your mass. So that's why the table was close. But Henry Moseley discovered that if he organized the table by the nuclear charge, he called it, the positive force of what is the protons in the nucleus, if he organized it by number of protons or atomic number rather than by the atomic mass, a lot of those little inconsistencies in the table disappeared, and we got our modern periodic table. Now, in this chapter, one of the things you're going to need to know is be able to understand trends. Because the table is put together in a very organized way, there's patterns that exist in the table that allow us to do certain types of predictions. So you need to understand what some of the common trends are. Most of these are things that you looked at in pre-AP chemistry. So a lot of these will be a repeat of what you looked at last year. So you need to know what the trend is and be able to use it to predict. You need to be able to explain why the trend occurs. And then sometimes there are some common anomalies you should understand as why the trend goes wrong. So some of the things that you need to understand what the trend is and why it happens would be the size of atoms and ions. You should also be able to understand the trends in ionization energy, electron affinity, and metallic character. So all of these are things that you should be able to understand the periodic trends in. But one thing that's very important for this, especially as we start getting closer and closer to the AP test in May, is when you're dealing with explaining a trend, and this is something that's typically on the AP test somewhere. Somewhere in the FRQ section, there will be things that deal with periodicity, and they'll ask you about a trend, which is bigger or smaller, but then they will always ask you to support your answer with a why. Don't confuse the explanation of the trend with what the trend actually, or with why the trend is occurring. So you can't say fluorine is smaller than oxygen because it's farther to the right. That's what the trend is. The reason why deals with nuclear strength and so forth. So what's going on with nuclear charge? So don't confuse an explanation for a trend with what the trend is. It's a really common mistake for people to put in that explain your answer or support your answer, and they're never going to be given any credit for that. So you need to make sure you're actually giving a why reason, not just stating what the pattern is. So be careful of that. Now, one of the most important things about understanding pattern trends is really understanding effective nuclear charge, which last year we talked about as nuclear strength. So we're talking about the same thing here. Now, in a many atom electron, electrons are both attracted to the nucleus and repelled by other electrons. Those two competing forces are incredibly important to behaviors and trends. You need to understand opposites attract, like things repel, and stronger attraction is a lower potential energy, more stable situation, and greater repulsion is the exact opposite. So it's all about maximizing attractions and minimizing repulsions. That's going to give you a more stable situation. So those are key ideas. You're maximizing attractions and minimizing repulsions, and that's going to be a guiding principle behind a number of the things we look at here. Now, the nuclear charge that an electron experiences really depends upon both factors. So nuclear charge would be how strong the nucleus is holding on to electrons. That's really what we're looking at with effective nuclear charge. Well, attractions and repulsions can have an effect on that because the strength of the attraction is really what we're talking about. That's an opposite attraction, positive and negative, but that can be impacted by the repulsions of the other electrons around that electron. So both play a role. So it's really about those two competing forces. Now, effective nuclear charge is the net positive charge experienced by an electron in a many electron atom. So when you consider both forces, the attraction and the repulsions, overall, what would be the rating of that nucleus? That's effective nuclear charge on an electron. Now, the effective nuclear charge is not the same as the charge, and that's because inner shell electrons and that repulsive force that they create. Inner shell electrons basically are a competing and repelling and a shielding effect on those outside electrons. And you may remember that concept from last year, what we called the shielding effect. Inner shell electrons interfering with the ability of the outside electrons being held onto by the nucleus. So effective nuclear charge is really looking at big picture what's happening. Now, the electron is attracted to the nucleus but repelled by the inner shell electrons, and those shield or screen those outside electrons from feeling the full effect of the nuclear charge. And that's why you look at what the strength of the nucleus is and then take into account how many core electrons you have, the electrons in between the outside electrons and the inside electrons, because your core electrons are the ones that are going to have the most effect on screening or shielding those valence electrons. So the shielding effect or the screening effect is really what we're looking at here. So those inside electrons have an effect on the overall strength of attraction of the nucleus. Now, if we're looking at a simple way to calculate effective nuclear charge, or Z sub EFF, that's basically just effective nuclear strength. You take a look at Z, which is the atomic number, and remember, atomic number tells you the number of protons, and then you look at the screening constant, which is closely related to the number of inner shell electrons. Now, there are more complex ways to do this, but what's shown up here is really one of the quickest, easiest ways to look at effective nuclear strength. It's oversimplifying the process, but in most situations, that's really what we're looking at. That oversimplification is perfectly valid. So because the valence electrons have some probability of being inside the core, remember from chapter 6, we talked about they live inside their apartment 90% of their lives, but they visit those inner shell areas all the time. So because they can actually be inside the core, the effective nuclear strength is usually a little bit greater than you think. So like in the case that's shown up here, nucleus is a positive 11. We have 10 core electrons, so the difference between those two is a plus 1. Well, realistically, because sometimes that valence electron is sometimes not being shielded because it's within the core of electrons and close to the nucleus, your effective nuclear strength is going to be just a little bit greater than 1. But this gives us a quick, simple way to comparatively look at what's happening with effective nuclear strength. Now, what the trend is. Now, when you go across a period, when you go across a period, you add a valence electrons, and valence electrons aren't in the core, so they do little to affect screening. So the effective nuclear strength is going to increase across a period because you're adding more protons as you go across. That's increasing the nuclear charge, but your screening a constant isn't really increasing all that much. So the most important thing about any across trend is that the nucleus is effectively getting stronger. And that's a core idea. You need to know this. This is the single most important thing about what happens across any period on the periodic table. So as you go across, you're adding protons and electrons, but the electrons aren't core electrons. So they're not doing much to screen. So as you go across, effective nuclear strength is increasing. Now, when you take a look at what's happening down a group, usually we don't really worry too much about effective nuclear strength. Now, some books will say it's constant. Some books will say, it decreases slightly. I've even seen, some books say it increases slightly. The actual answer, if you really look at actual values for nuclear strength, what is the rating of that strength on a valence electron, you'll see that it does actually increase slightly when you go down a group. And that's because you've got a larger electron core, and the bigger the electron core gets, the less effective it is at shielding. If it's a tightly compacted core, it's much better at shielding than if there's a lot of space in between. But really, the changes are not all that relevant, because what's really important when you go down is all about the increase in N. As you increase energy levels, you're farther from the nucleus, and distance kills attractive forces. So when you're really looking at, not how strongly could that nucleus hold on to electrons, but realistically, how big of an effect is it, because it's a very, very distance kills attractive forces, and that valence electron is now farther away. That has really a bigger impact than what's going on with the strength of the number of protons and the amount of shielding that you have. So realistically, what's important when you go across, you better know effective nuclear strength increases and why. Your nucleus is getting more protons, and the valence electrons that are being added don't do much to screen and prevent the increase in nuclear strength. But when you go down, it's really not all that relevant. So don't worry too much going down about effective nuclear strength. Really what's happening when you go down, it's all about adding energy levels, and that's a greater distance from the nucleus. So sizes are going to go up, and how strongly you really do hold on to outside electrons, and how strongly the nucleus holds on to electrons and other atoms and so forth. That distance kills the attractive force, and that's what's more important. So when you're going down, it's all about N increasing, not about effective nuclear strength. Now, why are energy levels not degenerate? This is actually something that I talked briefly about in the last chapter. And the big answer here is, when you have more than one electron, those repulsions complicate the picture, and you no longer end up at the same level. And one major component to this is the fact that when you're farther away from the nucleus, um, and how the nucleus holds on to different types of electrons, it's going to be slightly different. So effective nuclear charge is actually related to this whole idea about why you end up with degenerate level or non-degenerate levels, why they're not at equal energy amounts anymore. So in terms of energy, one thing you really should understand is the N level. So let's say we're on the fourth level. The fourth level S is lower in energy than the fourth level N, which is lower in energy than the fourth level D, and lower in energy than the fourth level F. So this would apply to basically any level where you have all of them. So on the second level S is lower in energy than the second level P. Well, that's really related to what's happening with effective nuclear charge, and it's not just about nucleus, it's also about the screening that different electrons undergo based on the other electrons around them and how much they penetrate close to the nucleus. So effective nuclear charge is actually related not just to trends on the periodic table, but also to our off-bow chart that we're looking at. Now, one of the things that is commonly misunderstood, and this used to be something that was often asked on the AP test, I haven't seen it as recent, but that doesn't mean it's not going to come back again. It's one that students often gets wrong. Why is the 2s lower in energy than the 2p? Well, people's gut reaction from all they've really thought about is they see that the energy is higher, so that must mean it's actually farther away from the nucleus. And that's not technically correct. If you actually look at the distance from the nucleus in angstroms for a 2p electron versus a 2s electron, um, you'd be wrong in saying that the 2p electrons are farther away from the nucleus, and that's why it's higher in energy. What you really have to understand is that's a misconception. The 2p is not higher, or I should say farther away from the nucleus than the 2s. If you actually look at the average distance, you'll notice that this hump is shifted farther to the right than where this hump is. So if you're really looking at kind of the average distance from the nucleus, the 2s electrons are actually farther away from the nucleus. So it's not that the 2p electrons are farther away from the nucleus. That's not why they're higher in energy. What you really need to understand is the 2s electrons and what they do. Got to get back to it. What they do right. Wow, it's flipping through there fast. What they're doing right here, while overall they're farther away from the nucleus on average, they have this little bump right here, which does have an effect on the average. But realistically, what happens is there is a period of time where those 2s electrons are significantly closer to the nucleus. And those two s's penetrating very close to the nucleus are less effectively screened. And that's going to increase the effective nuclear strength. And that's going to pull those electrons in, and it also means those electrons are going to be lower in energy. So the greater attraction um, of the lower overall energy 2s electrons is really why it's lower in energy. So it's not because the 2p electrons are really farther away from the nucleus, it's that the 2s electrons penetrate much closer and therefore they're not being screened as much. So be careful. Don't say the 2p is higher in energy because it's farther from the nucleus. It's really the 2s electrons are lower in energy because they penetrate closer to the nucleus, and that decreases the screening effect. Now, next section gets into our actual trends. And remember, we're going to apply ideas that we just talked about with effective nuclear strength here. First off, what happens with size of atoms and ions? Now, the bonding atomic radius, because there's different ways to measure atomic radius. Bonding atomic radius is defined as 1/2 the distance between covalently bonded nuclei. And we can actually use experimental techniques, X-ray crystallography, and show force to actually determine what these distances are. But since they don't really have an outside, if we took that diameter and cut it in half, that would give us an approximation of what the outside of an atom would be. So one way to calculate atomic radius is with bonding atomic radius. But realize that bonding atomic radius is actually slightly smaller than the non-bonding atomic radius would be. Now, trend in atom size. If you remember from last year, your bonding atomic radius, or just your atomic radius, is going to decrease from left to right. So atoms get smaller in general when you go from left to right, and that's because of increased nuclear strength. If increased nuclear strength is pulling on those valence electrons harder, it's going to pull them in more closely. So when you go across, atoms get smaller because of increased nuclear strength. That's all you got to for your reason. Now, it increases when you go from top to bottom. And remember, effective nuclear strength kind of irrelevant when you go down. What it's really about is due to the increasing value of N. As N increases, you're farther away from the nucleus. That's a larger atom. So across it was about effective nuclear strength, down it was all about N. Remember that. That's a core idea in a number of our trends. Now, ion size. It really depends upon the nuclear charge, the number of electrons, the orbital in which the electrons reside. There's a number of different factors because when we've changed the number of electrons, we're putting them into different regions of space than we put them before. So ion size is a little bit more complicated in terms of what it really is, but honestly, the actual trend is still just as the same thing as it was before for the exact same reason. Cations are smaller than their parent atoms. That's one trend idea you should understand, how the cation and anion compares to the size of the original atom. The other trend is what's happening when you go across and what's happening when you go down. So the first one we're going to look at here is what happens when you form a cation. Well, remember cations are formed when you remove the outermost electron. Well, what's going to happen then is that's going to lower the value of N, so your remaining electrons are closer to the nucleus, so your new highest level is going to be closer to the nucleus. And remember also the repulsions between the electrons are reduced. If you have fewer electrons, that's minimizing electron repulsions. So that means the nucleus is going to have a greater effect in pulling things in. So in general, what happens is when you remove valence electrons, you get a significantly smaller substance. So cations are always smaller than their parent atoms, and if you look at the sizes here, they're significantly smaller. Anions, on the other hand, are larger. And it's not because you're adding to a new higher level n. It's really about in the same general region of space, you're cramming another negative thing in there. That's going to increase the repulsions, which causes the electrons to drift a little bit farther apart. So anions are larger because of the increased electron repulsion when you add more electrons. So don't try and say anything about n. It's not relevant when you're talking about anions. Now trends, they're going to increase in size as you go down a column, and that's due to the increased value of n. So when we're talking about going from one cation to another cation in the period below, now we are definitely increasing for both cations and anions the value of n. So remember down, about the value of n. And when you go across, ion sizes are going to decrease. Now, this is cations decrease and anions decrease. We're not comparing cations to anions here. And remember, that's due to the increasing effective nuclear strength. Even though we've got different numbers of electrons as you go across, the effective nuclear strength is still increasing. That's going to pull those electrons in, making a smaller radius. So across, still about increasing effective nuclear strength. Down, still about n, just like it was with the atom. Now, last thing I want to mention, because this really finishes the notes from day one here, is the concept of isoelectronic series. It's something that students often have a hard time understanding really what it is. Now, what you need to understand is iso means same. So isoelectron means same number of electrons. So if we're looking at an isoelectronic series, we're looking at a group of substances, and they're going to be atom and cations and anions that all have the same number of electrons. So for example here, the isoelectronic series that we're looking at is involving sodium ions and magnesium ions and aluminum ions, and then oxide ions and fluoride ions. Now, if you take a look at sodium, based on where it's on the periodic table, sodium has a very specific number of protons and electrons tied to its atomic number. Sodium itself has 11 electrons. When it becomes Na+, that means it's lost an electron. Now it only has 10. Well, magnesium, based on where it's at on the periodic table, atomic number 12, it's got 12 electrons. So the magnesium 2 plus ion has lost 2 electrons. It also has 10 electrons. Aluminum is 13, and as a plus 3, it's 10. So each one of these has 10 electrons. That's an example of what's called an isoelectronic series. Now, how can anions be involved in this? Well, if you look at oxygen, oxygen has 8, so O2 minus has picked up 2 more. It's also got 10. So this is in the isoelectronic series. Fluorine has 9, F minus then has 10. This is in the F minus isoelectronic series. So what we have is Na plus, an Mg2 plus, an Al3 plus, and O2 minus, and F minus. And the one thing that we didn't put in this is they're all going to be the same number of electrons as that noble gas they're all getting to, which would be neon. So every one of these is isoelectronic to each other. Now, this grouping is a bunch of ions that have the same number of electrons. So they would form an isoelectronic ion series. So isoelectronic is really meaning a bunch of things with the same number of electrons. And if you look at what's happening with their general sizes, as you're going from sodium to magnesium to aluminum in this isoelectronic series, you can see that the size is decreasing up here when you're dealing with the cations. And when you're dealing with the anions, it's also getting slightly smaller. Well, why are these things, even if they have the same number of electrons, getting smaller, just like the ions themselves would? Well, the reason is, even though they have the same number of electrons, they don't have the same number of protons. And that has an effect. As you're going to the right with those cations, even though you have the same number of electrons, you've got an increased number of protons in aluminum. That's a greater effective nuclear strength. It's going to pull in those electrons. So if you ever see anything about an isoelectronic series, it just means a group of things with the same number of electrons. That's all it means. And we can also look at a trend within an isoelectronic series. And that ends our notes over this section.